I am Stefan Dilhaire, professor at the University of Bordeaux, France. And we are here to introduce a new thermoreflectance setup called the POSH-TDTR. So TDTR is thermoreflectance, time domain thermoreflectance, and POSH stands for picosecond optical sampling for heat transfer analysis. So you can see the setup here is made of two lasers. One is the pump that focuses on the sample here and excite and heat up the nanomaterials, for example. And the second one is here to read the temperature that has been induced by the pump laser. So during the measurement, you can monitor the position of the two beams here on the screen, and the oscilloscope produces the signal that is recorded by the probe. So as we are going to superimpose the two beams here, you will see the signal growing here on the oscilloscope. The problem addressed here is how to understand the heat propagation in nanolayers and nanostructures. So this sample is covered by an aluminum layer, and under this aluminum layer there is a stack of different materials. So one laser is heating up the surface here, and the heat flows through the whole structure, and just by measuring the temperature with a second laser here on top, and by comparing to a model, we can extract all the physical thermal parameters. So the point here is how to get this signal quite easily for the customer. So you will see here there is no signal at all because the two pump and probe beam are not superimposed. As soon as you are going to superimpose them, you will see the signal will appear here on the oscilloscope. So here you see I'm moving one beam with respect to the other, and you see the signal is coming here because we are getting closer and closer to the heat source. And as soon as we are totally superimposed here, you get the maximum signal here. And you see in real time the acquisition of the signal here. So the second step will be to record this and to get into the computer in order to, the third step, to do the optimization and to superimpose the model and the measurement. The main application of this concerns the knowledge of the thermal property of material at nanoscale. Because when people do simulation, most of the time they use the bulk values. They don't know what's happened at nanoscale. So there is a lack of tools to access these thermal properties at these scales. And there are only two tools to access these scales. One of them is a contact technique named scanning thermal microscopy. It's an IFM-based technique. And the other one is a contactless, such like TDTR and POSH-TDTR. With the use of this, you can put the results you get from that. You can feed the simulation software like ANSYS or COMSOL, for example. As soon as you are recording your signal, then you can move to the second software for the identification. So the model depends on a set of parameters you can see here, and is described here on the right. So you can see the laser that is focused on top of the surface, and the heat flows through this entire structure here. And you see that this structure is described by the set of 15 parameters that you can see here. And of course, you are not going to identify 15 parameters at once. You need to fix part of them. For example, the thicknesses or the heat capacities. So just via click here on that, you choose the parameter you want to fix, and you let free the other parameter here. And just by doing this, you can move to data you want to make the optimization. So first you need to find your file on the disk. As soon as you are ready, you move to the optimization. And here, you just need to click this, and you will see a set of parameters just after a few minutes. Here we are done. Here you've got your set of parameters by order here of appearance in the sketch you see here. And you see that there is a very good fit. This is a residual, better than 1%. And you can see that the fit works from the picosecond time scale here up to the nanosecond time scale. The point is here, when people want to predict the behavior of electronic component, for example, there are really tiny hotspots at the nanoscale with a very strange behavior because Fourier law does not exist any longer. So physical processes are very different. So you need to identify many things, like, for example, the effective thermal conductivity of very, very thin layer or the interfacial thermal resistance. And there is no other way than this contactless technique to access this. And as soon as you get this, you can feed your model and to make some reliable prediction.